There's some talk of batteries doing synthetic inertia, but it really doesn't, it's not the same thing, and it impacts that battery's ability to do other things. So in some places like Australia, if you want to build a new solar farm, you have to bring in a synchronous condenser, which is just a spinning hunk of mass. It doesn't provide any energy. It's just providing inertia. Yeah. Our motors and generators provide that in plenty. So we give that as a service for free, just like a gas plant would give it for free today on the grid. So in markets that are heavy renewables, this is becoming something that they desperately need and are willing to pay for.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. I'm here today with Curtis VanWalleghem, the co-founder and CEO of HydroStore, a company with a novel approach to utility-scale compressed air energy storage. This is important because it can be used like a big battery to even out the intermittent supply of renewable energy from wind and solar. Kurt founded HydroStore in 2010 and currently has a utility-scale system commercially contracted in Ontario, Canada, and gigawatts of projects in the pipeline. So they're already out there doing this for real, which is super cool. Kurt is an industrial engineer by background, and before founding HydroStore, he worked in management consulting, where he advised some of the top energy companies in the world. He also worked at nuclear and wind companies, including Bruce Power, which is the world's largest operating nuclear facility. He's based in Ontario, but has worked in more than 10 countries, including time volunteering in India. And in college, he was a varsity hockey player at the University of Toronto. Kurt, it's an honor to have you. Thanks for being here.
Excellent. Thanks, Dylan. Really looking forward to the discussion today.
So I'm curious, you had all this time at Deloitte in management consulting. I'd love to hear how you went from that to starting HydroStore back in 2010.
Yeah, I think, at management consulting, we were doing project turnaround. So I was always in and around capital intensive industries and seeing how those projects are managed and the impacts of those projects. And that really led me into the role at Bruce Power, where I was the head of planning and capital and operating budgets. And it was really when I was at Bruce Power that I saw the impact on the grid of intermittent wind and solar and how we were being asked to solve it. And I said, geez, every grid around the world is going to have this problem pretty soon. There's got to be something other than pumped hydro and strung together, essentially cell phone batteries. And then my co-founder had this idea that really, if pumped hydro is lifting water up in air, what if you put air underwater and you get the buoyancy force? And that's really where the idea started. And once I kind of ran the math, I said, this has a real potential to be compelling from an economic performance perspective. And I think the market's going to be huge because wind and solar costs continue to come down. So took the plunge back in 2010 to try to make a company of it.
And what was the industry like back then? I certainly wasn't working in this space, but if you look at kind of solar and wind adoption then versus now, it was like relatively quite nascent.
It was absolutely a nascent industry at the time. I mean, in Ontario, we're unique because we have about 50% baseload nuclear and 40% run-of-river hydro that's essentially baseload. So when they started adding wind and solar, we saw the impact of the intermittency pretty pronounced. But I think it was even in 2012 when the first storage procurement started to happen, and it was for flywheels and PJM for 5 minutes. And then it creeped up to an hour, and then it was 2 hours. And then California came out with a 4-hour mandate. Now there's 8, 12, 100-hour mandates coming out in different pockets of the world. So it's still in the early days. And part of the reason is, until wind and solar make up 30, 40, 50% of your kind of non-baseload generation, you really don't need long duration storage. But more and more of those grids are hitting that tipping point now. So I think we got another 10, 20 year of big time growth ahead of us for the industry.
And at that time, was it kind of clear to everyone that this is where this was going, and grid scale energy storage would be a really key component and was a great kind of place to be investing time and energy? Or were you sort of out ahead of the curve a bit on that?
I think I was a bit ahead of the curve. I think intellectually people could understand their intermittency of wind and solar. You're going to need something to firm it up, but it was such a far off concept. How do our markets change? When are buyers going to buy this? Do they buy it with wind and solar or not? So there was a lot of uncertainty as to when the market would form, which made raising capital was pretty challenging, I got to say, in those early days.
Okay. I do want to get into that at some point as we chat, the sort of raising capital and how you found success in that. I think just to kind of set the stage for everybody, I was hoping you could like walk us through how your system works and what the solution is.
Certainly. So we use compressed air energy storage. All the components are pre-existing, and I'll just kind of walk through the process in somewhat of a simplified way. But as you mentioned, there's an explainer video on our website. So we turn on a compressor. These are centrifugal compressors. They're used to compress natural gas down the pipelines, but also for LNG. But instead of compressing natural gas, we grab atmospheric air, pressurize it. Every time it comes out as hot air, about 200 degrees C, and now under pressure. We go to about 60 bar of pressure, 3 stages of compression. Each time you compress it, it comes out at 200 degrees C. We then run it through a shell and tube heat exchanger to pull the heat out, cooling the airstream to about 40 degrees C and 60 bar. That air then gets sent deep underground. We mine out a shaft, we put a shaft down and we send workers down, miners, and they mine out a hole in rock. This is 2,000 feet underground. Essentially a cubic football field is the size of the cavern, and that's for about 5 gigawatt hours of storage. And as the air gets sent down to the top of the cavern, otherwise it flooded that cavern with water. It starts pushing the water down, and it goes down a gooseneck and gets lifted up to the surface. So we're using air to lift the water 600 meters or 2,000 feet. So that water head is what sets the pressure at roughly that 60 bar. And a valve holds the air in, and the hot water the heat we store in hot water at 200 degrees C in an LNG sphere wrapped in insulation. So now you have a pressurized air, 2,000 feet underground, and a thermal mass of 200 degrees C water kept in liquid form under pressure. And then when the grid needs power, the valve simply opens, gravity pulls the water down from the reservoir, pushes the air up, it goes back through the shell and tube heat exchangers, reheating the air close to 200 degrees C. And then it drives a turbine, which is just a steam turbine. And the air goes back to the atmosphere, and the grid gets power on demand. And that's really as simple as it is. It's the only moving parts really are a compressor and the turbine. Then you have a shell and tube heat exchanger, hot and cold tank, and a hole in rock, 2,000 feet underground. And you got a really long life, robust system for energy storage.
Yeah. It's partially kind of compressing air in this cavern as a way to store energy, but also a thermal energy storage at the same time.
That's right. It's a mix of the two, and keeping those in balance is one of the secret sauces of HydroStore. And you can imagine if you need to add an hour, so if you have an 8-hour system and you want it to be a 9-hour or a 20-hour system, all we have to do is make the cavern a little bigger. It's linear, so you double it in size, you have twice as many hours. And then your hot tank, you need a second hot tank to double the capacity. That is a very low, it's about a $40 a kilowatt hour of storage capacity, marginal cost. Adding an hour of lithium ion is about $350. So it is dramatically lower cost to add hours, which is why we focus on longer durations, and batteries are better fit for shorter durations, because our first hour costs a lot more than a battery. Our first hour might cost $1,500. And a battery's $350. So if you only need 1 or 2, your better battery. Once you start needing 10, 15, 20, you're clearly better off with a solution like ours.
And can you say a little bit more about that? Like in what scenarios are longer duration solutions important than shorter relative to shorter duration storage?
Yeah, there's so if you want grid stability, frequency regulation, that you need 15 minutes or an hour. Then if you want to really shave the super peaks, you might only need 2 to 4 hours. Both of those applications are better for a battery. Once you start getting to reliability services, stuff where you need reserve capacity, but you're not always trading it, it's more sitting there as backup plants. That's really where you start getting more into a solution like ours, where you're doing arbitrage and you're sitting on reserve capacity, providing reliability services. Then you get into other solutions, which are just pure backup power. They're only used once a month or something. That's not really a good fit for us. There's other technologies there as well. We're kind of that intraday workhorse that you're charging and discharging every day, leveling the peaks and valleys, and keeping a little bit in reserve in case a coal plant goes down or a gas plant goes down. You're stepping in with some reliability capacity.
And so the kinds of things that are happening in the real world to sort of necessitate this would be like a cloudy day where solar isn't as productive and you're trying to compensate for that and deploy energy back on the grid, or what sorts of kind of real world events are we talking about compensating for?
Yeah, so it's a combination of arbitrage. So again, when it's really sunny out, prices might be zero. We'll use that to charge. And then when the sun's going down, rather than dispatch a gas plant, we can give you that peaking power back cheaper than a gas plant without the emissions. So that's kind of that daily leveling of the peaks and valleys. But then if something trips, right? So you're leveling the peaks and valleys, but you don't have much, you've done that for 4 or 5 hours. And then all of a sudden a gas plant trips or a transmission line gets knocked out. Then they say, we need more capacity. We can then keep giving that to them for another 5, 6, 10 hours, however long they've contracted us for. So it's really that blend of that daily leveling the peaks and valleys and sitting on some reserve capacity to help in case there's an outage or something else goes down.
And was this the solution you started with, or did you look at other ways to kind of solve the problem initially?
Oddly enough, we did have a different approach to the same fundamental physics, this hydrostatic compensation, storing air at a constant pressure. But we were doing it by sinking balloons under lakes and oceans and affixing them to the seabed and then running an airline back to shore. And so we built one of those in Toronto. We secured a contract in the island of Aruba. But as we got into construction and detailed design, it became clear that the costs of marine construction and the challenges of running an airline back to shore with the waves crashing, you just couldn't be cost effective at the scales that we were looking at. And that's when we really pivoted to this mining out a hole in rock and flooding it with water, and then using that at much bigger scale. Our typical projects are 200 to 500 megawatts now. When we had balloons under the water, we were looking at 5 to 10 megawatt solutions.
I see. So that scale can kind of justify the construction costs and everything.
Exactly. Like a project for us is, call it $1.5 billion to construct a 500 megawatt plant. Everything underground is only about 300 or 400 million. So it's not much, but if you think of it, if you grab a couple dozen miners and some trucks and some lifts and some explosive equipment, and you say, take 3 years and here's $400 million, mine me out a cubic football field deep underground. They're like, this is easy peasy and no problem. And that it just takes a while. It's not complex and it's not that costly to do. But you do need to do it at a fair scale to justify it.
Okay, so this is good because I had envisioned this being that you're finding kind of naturally existing caverns underground. You're building your own air reservoir.
Absolutely.
The big problem reservoir.
Yeah, the big problem with pumped hydro is the sites are so rare, and with the grid today, it's tough to get interconnection capacity. So for us, we knew that we had to be flexible siting, go to where the grid needs storage and where you can get interconnection capacity. So that site flexibility was of paramount importance. Our rough math is we can go to a third to the half of land mass or of substations on Earth where we can build within a few miles of. So great siting flexibility, and we're very compact relative to pumped hydro. So it's a big thing. If you were reliant on pre-existing caverns, it'd be pretty limited number of sites.
And so what are your site requirements? I mean, you need some land, just sort of square footage on the surface of the earth, and then certain geologies you're looking for?
That's right. So the main siting criteria are interconnection. So you do have a place to plug into the grid there. Then we need about 100 acres for a 5 gigawatt hour project. So it's, reasonably compact. I think if you did it with lithium ion batteries, you'd probably be in the same footprint, if not more. And then 2,000 feet underground, you want hard, stable rock. That's kind of the siting criteria. We don't need access to a lot of water. We use about 1/20th the water of a comparable pumped hydro plant. And every day we operate, we make water out of fresh air. Because when you compress air, it knocks out the moisture, which is more than we lose through evaporation. So we can go in the middle of a desert, one-time fill, and then we produce water as we operate. So it is reasonably, and it's closed loop. It's pretty easy to permit. So, quite flexible on the siting front.
And then, actually, I'm glad you mentioned evaporation, because that was one of my first thoughts. Is like so if you look at a picture of your site, you have this kind of pond or reservoir that's open to the air at the top. But that's interesting that you can kind of make up for the evaporation just by the air you get or the water you get from the air.
Yeah, and you compare that with pumped hydro. Again, they'll have a reservoir 20 or at least 10 times the size, but they have 2 of them, and both of those are evaporating constantly, and they don't produce any water. So they have to be constantly topping up the water, which really limits them to go to a place like California or the deserts in Australia or something like that.
I'm curious, has that been is that in reality a big differentiator for the technology? Is the water kind of water use a challenge for pumped hydro?
Yeah, well, it's becoming more and more of a challenge. Pumped hydro in California is a virtual impossibility. And so water is a big drawback. And when we engage with the NGO, the environmental NGO community, our lack of need for water and our real limited usage is a big differentiator. And I know if you go to certain places that are water starved, they're never going to let you build pumped hydro. Our system can indeed get that social license in those markets.
I'm curious about just like the caverns themselves. Do you do anything to treat them, or is it just sort of naturally airtight at 60 bar? Like you don't get a lot of pressure loss?
Yeah, that's exactly right. So we go in competent hard rock, but if you think about it, the groundwater is trying to come in, and the groundwater goes up to almost the surface in most places. So you've got groundwater trying to come in, and it's frankly under that same pressure, and the cavern's trying to collapse on itself. We're more like propping it open and pushing out the groundwater. And so to think that limited drive pressure can move air through cracks 2,000 feet through hard rock is very, very limited. Because it's just air and fresh water, we can afford some leakage if there is. But no, they just go in, they mine out the caverns. They'll make it like a waffle pattern of tunnels or drifts. And then they may grout any seams that they see. But as long as there's not groundwater flowing in, because that would tell us then our air would flow out those same seams, we just grout up any of that stuff. They'll put in some rock bolts to make sure no roof sloughing events kind of happen. But otherwise, it's literally just a hole in rock, about 40-foot high tunnels.
And then do you monitor them over time?
We don't. So there's about 300 of these caverns in the US storing butane, propane, natural gas, and they've been operating for 70, 80 years. They're designed that you never re-enter them because they have that hydrocarbon in them. For us, we could re-enter, but there's really no need to. We can send drones down there, either when it's filled with water, swim a drone down, or drop one down when it's filled with air. So we can monitor, but we mostly just monitor the flow of air and water in and out to ensure that the capacity stays the same. And if there is any leakage, we detect it more from the surface, measuring the flow of stuff in and out.
What are some of the kind of technical innovations or challenges you've had to overcome that would be interesting for engineers to hear about?
There's probably two I would highlight. The first one is the air thermal balance, because we are storing a lot of our energy as heat, thermal mass, but we also have a compressed compressed air, the potential energy there. You've got to keep those in balance, because you need, every time you're compressing, you're producing heat and air. You got to keep those in the rough same balance, because on the way out, if you don't preheat the air, it'll go cryogenic when it's going through that steam turbine and ice it up and stop it from being able to run. It'll go cryogenic. And when you're running a half cycle, you start up, there's transient losses as all the steel's heating up. And so you've got to be really careful to manage. You don't have too much heat or not enough heat or too much air. And so managing that and being able to interpret from how much heat you have and the flow of your air, what is the capacity state of charge of the battery? How much energy do you have that you could offer the market when you're doing all these partial cycles, charge, discharge, and whatnot? So that was one that we had to work pretty hard on. We operated a pilot plant for 5 years to optimize the thermal management and that air heat exchange. Then we built a commercial reference facility, and we've been running that for about 4 years. And then we've obviously done all the modeling work on the scale plants, which we're just entering construction on. So that's the one, is just the control of the air and thermal, which is not the same for like pumped hydro. They only have potential energy and water. So they don't have to keep anything else in balance. The next one is a bit more exotic. It's called the champagne effect. But it's really when you have high pressure air in contact with a fluid, the air will dissolve into the fluid. And if it then chases down our gooseneck and up that shaft to the reservoir, as those air bubbles start getting under less pressure, they start expanding. And then you can imagine at the top, at the surface, if you had all those bubbles coming up, it would look like you popped the top off of champagne, and a bunch of air would start spewing out. And if that ever did connect to the main air cavern and made an air channel, that would essentially lead to like a well blowout type situation, which could have some pretty catastrophic complications.
And you'd lose your pressure, right?
You would lose pressure, and it would have safety issues, and there would be a lot of challenges there. Not something we ever want to see, which is why we had to prove to the regulators and the permitting agents why this will never happen with our system. And we've designed and patented solutions that will guarantee that won't happen. And some creative ones, like we have a whole bunch of layers of redundancy. One of them is just you make that gooseneck at the bottom, that U-trap, really deep. And in doing that, it's harder for those bubbles to chase down because it keeps getting more and more pressure as you get deeper. The second one is we have a downcomer up at the top where we're injecting fresh water into the top. So you kind of dilute the effect, if you will, and you can control how much you dilute it. So if you were ever seeing air or water coming up that was somewhat saturated in some air, you could then start pumping fresh water down into that column to dilute that effect. And that gives you some control from the surface to overcome. You can also make the certain limitations on the compressor power and pressure that can step out of there. So there's a whole bunch. And like I say, we've got layers and layers of redundant solutions to make sure that never happens.
So that sounds like you must have some kind of real-time monitoring and control of these things.
That's right. Yeah, we put sensors everywhere, and that kind of master control system. It's kind of how we get that air thermal balance, but it's also how we monitor our system. We're measuring flow rates, temperatures, pressures, all over our system and in the water channel, taking samples, how much air is saturated in the water, not temperatures of water. There's a whole bunch of things we're measuring in real time constantly.
Super cool. I think you said you're building and maybe you told me this when we first met, a 500 megawatt project?
Yeah, we have a 200 megawatt, 8 hour, so 1.6 gigawatt hour project in New South Wales, Australia. That one we expect to start construction in the coming quarters. And then we have a 500 megawatt, 8 hour, so 4 gigawatt hour project in Kern County, just outside of LA. And we expect to start construction either late 25 or early 26 on that project.
Okay. Can you help us put those numbers into kind of some real world context? Like how impactful is a 500 megawatt project to the grid in terms of, I don't know if it's number of households or how you think about it. And then also just sort of what does a project of that size look like and cost?
Yeah, so 500 megawatts, 8 hours. That would be about a quarter of Toronto, the city of Toronto, 5-6 million people. That's just over a 2 gigawatt load from the city of Toronto. So we would do a quarter of the whole city, and we could sustain that for 8 hours before we have to charge up again. So it is impactful. It is meaningful on a city and a regional basis. It enables about 1.5 gigawatts of solar and wind coming onto the grid because you don't need one for one match. You get more renewables than you do the storage that kind of firms it up. It's about a $1.5 billion capital project, takes about 3.5 years to build, fits on a 100-acre site. And will employ about a peak workforce of about 350 people. And that's over that 4-year period. So in total, you get about, close to 1,000 person years of employment, which is almost all local. If you think about what we use local concrete, steel, local labor, union labor to work. And most of it is it's renting local equipment and it's local labor, drill, blast, get out the cavern and weld and commission and install the machinery, and then buy the local steel for the heat exchangers and spheres. So it is a very local, like I know in the US, there's talk of a lot of tariffs. They don't impact us at all. We are local. When we're in Australia, we build and buy Australian. Same within the US, same within Canada. So we drive a lot of local jobs as opposed to a battery that is at the manufacturing plant and just gets shipped to site and dropped down.
Mm-hmm. And then there must be some sort of ongoing operations and maintenance employment as well.
That's right. Our plants are designed to be fully autonomous. Our plant up in Goderich, Ontario runs itself, but we do have a full-time workforce. So we'll have 24/7 coverage, about 25 full-time employees, really just monitoring the situation, planning any preventative maintenance, that sort of thing.
And then what's the business model? It sounds like you're operating your plants. Are you buying and selling energy essentially?
So we have two sides of the business. The one is our development team that goes out, develops project finances, and then we're the owner operator of the plants. We might do that in partnership with infrastructure funds or other utility partners, but we are the technology provider, the operator, and we warrant the performance of the plant. The other side is when we would just license this design to a different utility that they want to build it and own it and dispatch it on their own. So the first model, we got to go get the PPAs. We got to make sure there's a construct to get paid and get a long-term contract so you can underpin the project finance. And you really have to build a few of those before a utility is going to be comfortable going to their regulator and saying, can I have $1.5 billion to build this compressed air plant and put it on my rate base or the consumer's rate base? They're not that big of a risk taker. So they want to see a few operating under a developed model. Then we'll shift more to doing both the developing and the licensing. But the focus right now is let's get a handful of these up and running at scale on our balance sheet, and then we'll license it to utilities.
Okay. They have to see a track record of kind of success and reliability and whatnot before they're willing to take the plunge into a new technology.
That's exactly right. And as I mentioned earlier, every component is off the shelf. The construction, you just use local construction labor. So we don't have any manufacturing facilities. We are essentially a systems integrator with a patent portfolio and a development team to bring projects together.
It sounds like that's kind of one of the ways you're sort of getting over that that hump of like how to get your customers to finance this. Kind of curious about like the unit economics and like the, I don't know, round trip efficiency and what do they call it? Levelized cost of energy storage. How does this compare? You mentioned earlier how much cheaper it is to add additional kind of duration relative to batteries. Where does this sit sort of economically with other storage options?
So we compare mostly with pumped hydro and lithium ion because they're the most common solutions out there. At 8 hours, we have about a 25% lower LCOS than lithium ion and about 15 to 20% lower than pumped hydro. Once you move to like 16 hours, we're about 50% lower than lithium ion. And again, about 25% lower than pumped hydro. For us, relative to pumped hydro, it's our ability to go where they can't go more so than our cost advantage. But with lithium, it really is a lower cost because we have a much longer life. Now, batteries are more efficient. We're about 65%. They're about 85%. They can be built faster. We take about 3 to 4 years to construct. They can go anywhere. We can only go to a third to half of landmass. And they can be built at any size. We have a minimum size. So there's still a lot of reasons why batteries are going to have a big run. But where we compete, where you do need 8 to 20 hours of storage, you need 500 megawatts, and you're planned far enough in advance that you can have a 4-year construction, we do offer a better, drives more local labor, lower cost, longer life, and we bring synchronous inertia because we use synchronous motors and generators. So we provide a lot of grid reliability services that batteries just are not very well placed to provide as well.
Okay. Can you explain that? What do you mean by synchronous motors and generators?
So the grid requires inertia at all times, and inverter-based technologies, solar and batteries predominantly, can't provide that. You need spinning mass. So it's historically been provided by coal, gas, hydro, and nuclear assets. But as more and more wind, solar, and batteries are coming on, they quite often don't have enough inertia. There's some talk of batteries doing synthetic inertia, but it really doesn't, it's not the same thing, and it impacts the battery's ability to do other things. So in some places like Australia, if you want to build a new solar farm, you have to bring in a synchronous condenser, which is just a spinning hunk of mass. It doesn't provide any energy. It's just providing inertia. Yeah. Our motors and generators provide that in plenty. So we give that as a service for free, just like a gas plant would give it for free today on the grid. So in markets that are heavy renewables, this is becoming something that they desperately need and are willing to pay for. In fact, we've been shortlisted for a contract in Australia to provide inertia services through our Silver City project.
Yeah, the other thing I was thinking about relative to batteries is, and you kind of mentioned this, is like performance degradation over time. Is actually pretty significant with lithium ion, is my understanding. That it sounds like what's the lifetime of a HydroStore project, and what does that look like?
Yeah, I think, lithium, they continue to get better, but in general, I think they're about a 15-year life that degrades at about 3% per year. So you either got to overbuild it at the beginning or have your contract continually derated or keep adding new cells as you go. And obviously that warranty assumes you run it exactly as the manufacturer spec'd with the right humidity, temperature, and you break any of those, that life can really shorten quickly. For us, it's a 100-year asset. Essentially, we'll warrant 50 years, zero degradation loss over that 50-year period. So it is we're like a perpetual asset, like a hydro dam is. Once you build it, it's there. You keep overhauling your compressor and turbine, but you can essentially keep running it forever.
Cool. What's your prediction for this market? What do you think the energy storage market will look like, and in terms of like how, will we have a diversity of approaches that are all sort of optimized for different sites and locations, or do you think we'll sort of consolidate down to like all HydroStore everywhere, or what do you think that looks like?
On the macro, I think as wind and solar keep getting added, the storage is going to, you need more and more storage and longer duration. So that's the trend that we're seeing is just a huge growth in the amount of megawatts, and the megawatts need more hours behind them. I think there will be a diversity of solutions. Clearly, lithium ion will do the short end of the curve. The long multi-day seasonal might be done by something like hydrogen or form energy or a thermal type solution. Then you have that interday, that 8 to 24 hour. In that, I think, flow batteries, maybe if they can get their costs down, definitely compressed air. There's groups like Energy Dome. There's new batteries coming out like e-zinc and Enervenue. There's some pumped thermal like EcoGen. So there's a whole mix. And I think some of them are better on efficiency. Some are better on getting built small. Some might be better at 20 hours, whereas others are better at 8. So I think there will be just a big mix. Sometimes if you need it on the distribution system, we're not an option. Therefore, a flow battery might be a little better. If you're an industrial customer, you might want something that can store heat and use that heat directly or convert it back like an Antora offers or somebody like that. So there's going to be a whole mix of different solutions. I do believe that we have the lowest cost, best overall value prop, but we're also the one that requires the biggest scale and the longest to build. So we're not going to dominate the market, but I think we will get a sizable share of it.
Can you quantify that a little bit? What is your vision for the sort of scale for HydroStore?
So we see ourselves at about probably 25-30% market share of that 8 to 24 hour market globally. That's not commercial, industrial, and residential. We can't do that small scale stuff. So that's kind of what we look at. And when you look, it's absolutely a massive market. We're talking hundreds and hundreds of gigawatts, which that was a multiple of our business plan if we're able to achieve it. We've put out a very aggressive, compelling business plan. And I think it's showing we're only getting about 5% of the market share we think we could ultimately earn. So it is a huge global market out there and is just getting started.
Awesome. Let's see, Kurt, I'm ready to move on to the last few questions, unless there's anything else you wanted to hit that we haven't talked about.
No, I don't think so. I think there's a long duration energy storage council globally that helps all the companies explain the value of storage, because we're really competing against, there's base load like nuclear and geothermal are clean electrons. And then you've got gas and coal that are obviously the emitting side, storage paired with wind and solar. That combination is really the path that I think is ultimately the lowest cost and going to deliver the most value to the grid. But we as a community kind of team up together under that long duration energy storage council to express our views and push forward the industry, which requires a lot of market redesign. You don't pay the same for a 2-hour battery than an 8-hour, than a 24-hour, but those market signals don't exist. Those products don't exist. So there's a lot of market design that needs to happen to pair intermittent renewables with the appropriate type of storage to allow the grid to be reliable. So that's the only parting thought I would say is just the importance of that market redesign and thinking well in advance. So you don't have the lights start going out, everyone blame intermittent wind and solar, therefore let's go back to gas and coal. I don't think that's the right answer, but it requires policymakers to think in advance.
And you're engaged in that directly.
That's right. That's exactly right.
No, I think that's a really interesting kind of dynamic I see in a lot of these companies where you're, in some ways, you're kind of influencing the future by, influencing policy and market factors and everything, and you're inventing the future, in that you're kind of, you're inventing the new technologies that sort of support these things. But you're also making a lot of guesses about where things are going to go. It sounds like a really kind of fun part of the job.
Yeah, it is. It does bring just one more risk element. So again, when we talk about raising capital and how hard it was, So the long-term nature of ours, the big ticket sizes, uncertain regulatory environment, uncertain demand. We don't know what the future is going to hold. Like, it was an awful lot for our investors. And I'm very grateful for all the investors that showed the faith and bought into our vision, and happy to be paying them back now.
Yeah, right. Sounds like it was the right call. Cool. I have 3 questions that I ask everybody at the end of each episode. The first is, how optimistic or pessimistic are you about the future of the planet, and why?
So I'm naturally an optimist. I think, obviously with the US election, COP29 not going that smooth, I do think climate change is going to get a lot worse before the global consciousness really wakes up and maybe make some of the tough political decisions. But I'm confident we will get there. I got a ton of faith in humanity, and I think that the trend, we're moving in the right direction, albeit too slow. I think that starts to speed up, and ultimately people will elect our political leaders that are going to make the changes necessary. As the storms keep picking up and the fires and everything else, I think it's just going to slowly start moving the electorate more and more towards those that will enact climate policies. So I'm cautiously optimistic, but I'm a little scared for my son's sake. I got to be honest.
Who's another company or individual doing something to address climate change that's inspiring you?
I would have to call out Greg Jackson at Octopus Energy, just doing absolutely fantastic stuff and breaking the mold of these utilities and how we pay for, adopt, and integrate. I just think, that they're doing policies like, if you allow them to be involved in designing the house, they'll give you free energy for 10 years. And they can use your heat pumps and your electric vehicles. It's incredible. Their software is lapping the industry, and I just see them taking over the world from a electricity dispatch perspective. And he's a great guy. So big fan.
Cool. Yeah, I've come across them, but I need to learn more about what they're doing. Thanks for calling them out. What advice do you have for someone not working in climate today who wants to do something to help?
I think, to be honest, almost every industry has a climate angle to it. Whether you're in real estate, greening the buildings, you're in aviation, sustainable aviation, even mining, they're electrifying everything. So I think no matter what industry you're in, there's an opportunity to bring sustainability and climate transition thinking into that industry. And I would just, every little bit counts. Just chip away, do what you can within your role. The core renewable energy sector is growing so much right now, especially with data centers and the load growth that they're bringing. There is no shortage of opportunities. And I think we need every smart engineer and non-engineer to get in the battle and help speed up this energy transition. Because once we have marginal zero cost energy for all on a reliable basis, it is going to unlock so much potential for mankind to do all number of things. Energy's been the limiting factor for a lot of progress and growth. And the good thing with renewable energy, it's clean, but it's also abundant, and dirt cheap. So we just got to get the transition done. So anyone chipping away, and if not, come to the growing sector. I know we've got dozens and dozens of open jobs at HydroStore.
Nice. Great. Yeah, great point. Kurt, that was really fun. Thanks a lot for your time.
Excellent. Thank you so much, Dylan. Really appreciate it.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.